Function notation is another way of writing an equation. Function notation defines the range or output, range, I'll just call it the output or value of the function by using any value of the domain, or x. If the equation is a function, then we substitute y with the expression f of x, and it's pronounced f of x. Okay, so for example, in this equation, y equals 3x plus 1, we would rewrite this as f of x equals 3x plus 1. Okay, so then to find the value of a function at a given variable or expression, we can analyze this using numbers, we can analyze it using variables, we can analyze it using expressions. We want to substitute either the number or the variable or the expression into the equation and then evaluate or simplify. Okay, so for example, we have f of x equals 2x minus 3. So to find f of, say, 5, I'm going to, now what I like to do is I like to leave a blank. I like to leave a spot for me to evaluate whatever it is in the parentheses that they're going to stick there. So instead of writing an x, I'm going to put a blank parentheses there, and then I'm going to fill the hole. So what am I going to write inside the parentheses? I'm going to write 5. And then I just need to simplify. So 2 times 5 is 10 minus 3, and 10 minus 3 is 7. Okay, so f of 5 happens to equal 7. Now, if we think about this, what that translates to is that translates to the ordered pair of, 5, comma 7. So when x is 5, y happens to be 7. Okay. We can also do this with a variable. So I can, again, I'm going to set it up where I leave a hole, and then I'm going to fill the hole up. So I'm going to write a negative x in there, and then I just have to distribute that. So 2 times negative x is negative 2x minus 3. So f of negative x is negative 2x minus 3. And there we go. All right, in this last example, we are replacing it with a variable expression, which sort of starts off the same. So 2 with a blank minus 3, and then I want to fill the hole. So I'm going to write x plus 1 inside the parentheses, and then I'm going to distribute that. So 2x plus 2 minus 3 at the end, and I can see there are like terms. So f of x plus 1 equals 2x minus 1, and that would be my final answer. When we look at more complicated functions, this same idea kicks in. We're still going to, I'm going to leave some space. Anytime I see an x, I'm going to leave a little blank there, a little parentheses, and then I'm going to fill the hole in with whatever the functional value tells me to. So anywhere I got a hole, I'm going to stick a negative 2 in there. And then I'm going to simplify from here. So what's negative 2 squared? That's 4. This is minus 6 plus 5. And then that would be, 9 minus 6. So that would be 3. So g of negative 2 equals 3. Okay, looking at the second part of this, again, I'm going to start up by putting a bunch of blanks, which is a great habit to get in, especially if you get confused by signs. And then I'm going to fill the hole with whatever they told me to, so I'm going to put a negative x in there. Negative x squared is just x squared. Let's see, 3 times negative x is negative 3x plus 5. And in this case, there's not much to simplify. Nothing at all we can do. So that is actually our answer. And in this last case, just start off with a slightly bigger hole, but I'm still going to have a hole, and then fill it up. So what am I going to stick in the blank? I'm going to stick x plus 3. Okay, now x plus 3 squared is really x plus 3 times x plus 3. So we'll come back and simplify this. This would be 3x plus 9 plus 5. Then I want to distribute the x plus 3 times x plus 3. So that would be x squared plus 3x plus 3x plus 9. Then we have the 3x plus 9 at the end, plus 5. I see several places where I can combine like terms. So we end up with x squared. Let's see. G of x plus 3 happens to equal x squared. Then I have 1, 2, so I get 3 of those, so there's 9 x's. And then the 9 and the 5 give me, let's see, oh, I'm sorry, the 9 and the 9 and the 5. So, wow, good thing I stopped and said that. Okay, so I got 9 and 9 is 18. 18 plus another 5 puts me at 23. And so that's our answer for that expression. All right, so now we got a good old fraction that we can do the same process to. And again, I find it helps to set up the blank step. So I've got something squared on top, something minus 1. And so what am I going to fill that hole with? I'm going to write a negative 1 both times. Okay, so up top we have negative 1 squared, which is 1. And then we have negative 1 minus a 2, so negative 2 in the denominator. So we end up with negative 1/2 as that one. Going to h of 4, so again, let me put some blanks in here. And what are we going to fill the hole up with? We're going to evaluate it with a 4. Okay, so I get 4 squared, so it's 16 over 4 minus 1, which is 3. And that's pretty good right there. So h of 4 equals 16/3. Okay. And then one more. So again, I'm going to start with my hole. And then what am I going to fill the hole with? Negative x. So negative x squared, that's just positive x squared. Denominator, there's not really anything to distribute, so that just ends up as negative x minus 1. And that's actually a perfectly fine answer. So h of negative x is x squared over negative x minus 1. And there we go. All right, the graph of a function is the picture that represents all these solutions or ordered pairs for the equation or function. Okay, so if every value in the domain, or x, corresponds to only one value in the range, or y, then the graph is a function. If any value in the domain corresponds to more than one value in the range, then it is not a function. So we got a nice easy graph way to identify this. So to determine if a graph is a function, we use the vertical line test, which states that if a vertical line intersects the graph at more than one point, the graph is not a function. Okay, so looking at these three illustrations then, I'm going to see these here. What I'm doing is I'm imagining that I take a vertical line and I'm going across the picture with this. So if I take any location and I just, think of a whole bunch of these things, what's the most that this particular picture is going to touch? The vertical line. That's going to be only once. So this is what's called it passes the vertical line test, and so it is in fact a function. Okay. The second example, I can graph multiple vertical lines, and I can see that there's violations all over the place. All I need is it to violate it once, and it's not a function. So the second picture is not a function. And then in the third picture, nice horizontal line there. So again, imagine if you draw in vertical lines all throughout the picture, you would only touch the original function once. So this is in fact a function.